Hello! In this lesson we will show what vector addition is, how to do it, and give you a small taste of what it is useful for. Let's start by looking at a geometric representation of two different vectors, which I will call u and v. We can clearly see their individual x and y components. So what does it mean to add these two vectors together? Well, geometrically we can take one vector and place it somewhere, and then take the other vector and place its tail at the head of the first vector, just like so. We then draw a vector that starts at the tail of the first vector and ends at the head of the second. That vector that we just drew, which I'm calling w, is the result of adding together u and v. Now, how do we know what the x and y components of the vector w are? Well, we see that if we were to just add the x components of u and v together, we get the x component of w. And if we add the y components of u and v together, we get the correct y component of w. So all vector addition means is that we add the x components of each vector together, and that forms the x component of the new vector. We then do the same thing for the y components. We can write that with this notation, where the subscripts represent which component, x or y. In our case, we add together the 5 and 3 to get an x component of 8. We then add together the 4 and the 2 to get a y component of 6. Therefore, w is given by 8, 6. Let's see how we can use vector addition to help us understand how an object moves in two dimensions. Imagine I drive a car and I start at a position given by the vector 10, 20 meters. R is often used to mean position, so R0 just means my initial position. I am cruising along with a velocity vector of 30, 40 meters per second. What will be my position vector after 2 seconds? So what we want to do is find out how much my position is going to change in 2 seconds because of my velocity, and then we are going to add that to my previous position using vector addition. So first, let's compute what my change in position will be. I denote this with a delta r, which means change in position, since delta means change. To do this, I multiply the 2 seconds by the velocity vector. Well, how does this work? It's really quite simple. When you multiply a non-vector by a vector, you simply multiply each component of the vector by that non-vector. So we multiply 2 seconds by 30 meters per second, and get an x component of 60 meters. We then multiply 2 seconds by 40 meters per second and get a y component of 80 meters. So our change in position vector is 60, 80 meters. We call the non-vector a scalar, by the way. What this does is it increases the size of the vector, but it does not change its direction at all, since each component is scaled up by the same factor. Before we move on to the next step, I would just like to say that if we were to divide a vector by a scalar, it's the same process. Divide each component by the scalar. In that case, you'll be reducing the size of the vector, but not changing its direction. Now, let's add our change in position to our original position. First, the x components. 10 plus 60 is 70, so that is our new x. And 20 plus 80 is 100, so that is our new y. So we have calculated that, after 2 seconds, our position vector will be 70, 100 meters. And that is all there is to it. Real quick, I want to show you another example, this time with acceleration. I am again driving with a velocity of 30, 40 meters per second. But this time, I am experiencing an acceleration in a very different direction than my motion. What will my velocity vector be in 4 seconds? If you think you can figure this out yourself, pause here and give it a go. We will first compute the change in velocity over those 4 seconds, and then add that velocity change vector into the original velocity. To get the velocity change vector, we multiply the acceleration vector by 4 seconds. Let's do that now. 4 times 5 is 20, and 4 times minus 10 is minus 40. The units of seconds from the time cancels one of the seconds in the denominator of acceleration, and we are left with meters per second. So we have a change in velocity vector of 20, minus 40 meters per second. Next, we add this to the initial velocity. 20 plus 30 is 50, and 40 plus negative 40 is 0. So now the new velocity vector is 50, 0 meters per second. So in this case, the acceleration changed the direction of the velocity, which means that acceleration can change the speed, but it can also change the direction. And that's it. Thanks for watching.